Welcome to our new derivatives module. We'll review finding maxima and minima and work on an optimization exercise. You'll need a grasp of elementary function derivatives and basic math operations. Let's begin with a review of the procedure for calculating function maxima and minima using the second derivative criterion. This involves start by finding the derivative, setting it equal to 0 and solving for the points. These points, where the first derivative equals 0, are known as critical points. Don't forget to include any points where the derivative is undefined. This is a crucial step. After determining the critical points, compute the second derivative and substitute these critical points into it. Depending on whether the second derivative is positive or negative, you'll identify relative minima or maxima, as shown on the screen. If the second derivative equals 0, then you'll need to apply the first derivative criterion. Now let's illustrate this with an example. This particular example was featured in the June 2014 exam, if my memory serves me right. Let's see this procedure in action. We start by taking the derivative of the function, which is a product of functions. When handling a product, we apply the product rule. This entails finding the derivative of the first function, x plus 1, resulting in 1, and then multiplying it by the second function without differentiation. Additionally, we add the first function without differentiation times the derivative of the second function. Be particularly cautious at this stage not to overlook the factor of 2. The derivative of e raised to the power of 2x is e raised to the power of 2x times 2. Where does the 2 come from? From the derivative of the exponent. When you differentiate e raised to a function, the result remains e raised to the same function, but you multiply it by the derivative of that exponent. In this case, it's simply e raised to 2x times 2. To emphasize, the 2 arises from the derivative of 2x. Now that we have this, what's the next step? We can factor out the common factor, which is e raised to 2x. This leaves us with 1, and here we have 2 times x plus 1. Be cautious when extracting the common factor, as that 2 was originally multiplying. It's easy to make a mistake and mistakenly write it as 1 plus x plus 1, overlooking the 2. I am left with e raised to 2x times 1 plus 2 times x plus 1. That simply results in e raised to 2x times 2x plus 3. It's not very complex. That's our first derivative. What's the next step? We set the derivative equal to 0 and solve the equation. In other words, we consider this equation. E raised to 2x times 2x plus 3 equals 0. As we've consistently emphasized, when you multiply two terms to get 0, either one of them must be 0. However, in this case, e raised to 2x is an exponential term, and there are a couple of important properties to consider. First, exponentials never cancel out, and second, they are always positive. Let's focus on the first property. Exponentials never cancel out. So what does this mean? If these two terms multiply to give 0, it's not because of e raised to 2x, but rather due to 2x plus 3. In other words, x is equal to minus 3 halves. To solve for x, we set 2x plus 3 equal to 0. We move the 3 to the other side by subtracting, and the 2 by dividing, which yields x equals minus 3 halves. Have we identified any critical points? Just one. Do we need to find more? Is there any point in this function where it's not differentiable? The answer is no. This function is differentiable at every point. E raised to 2x is differentiable at all points, and x plus 1 is a polynomial, which is also a differentiable function at all points. Consequently, their product is a differentiable function at every point. There's no need to add any more critical points. What's the next step? We must calculate the second derivative to determine whether this point represents a relative maximum or a relative minimum, or to put it more precisely, to find out whether the function reaches a relative maximum or relative minimum at this point. The first derivative is as follows. And now we proceed to calculate the second derivative using the product rule. The derivative of the first term is 2 times e raised to 2x, multiplied by the second term without differentiation, plus the first term without differentiation multiplied by the derivative of the second term. It's important to note that this 2 doesn't come from the derivative of 2x, but from the derivative of the second component, which is 2x plus 3, and is equal to 2. We can extract the common factor of 2 multiplied by e raised to 2x. This leaves us with 2x plus 3 plus 1, which simplifies to 2x plus 4. This is the second derivative. What's the next step? Let's substitute the critical point we found into this derivative. Notice that if we replace x with minus 3 halves, we get 2 times e raised to minus 2 times 3 halves. The negative sign is brought outside, and the two 2's cancel out, leaving us with just e raised to the power of minus 3. Similarly, when we substitute x with minus 3 halves, the two 2's also cancel out, leaving us with minus 3. Adding minus 3 and 4 results in 1. In conclusion, after simplifying, we are left with 2 times e raised to minus 3. It's positive because we established that exponentials are always positive. What does this imply? it means that the function attains a relative minimum at x equals minus 3/2. And the value of that minimum is simply minus 1/2 times e raised to minus 3. How did we arrive at this value? We went back to the original function and replaced x with minus 3/2, yielding the result of minus 1/2 times e raised to the power of minus 3. Graphically, we can see that the relative minimum is reached at minus 1.5, which corresponds to our earlier result of minus 3/2. There are no other relative maxima or minima in the function. We've gone through the fundamental steps for calculating relative extrema and some basic derivatives. I hope this knowledge will prove valuable in the future. Thank you.